Hello.
Hey, Beer.
Hey, Corey, this is Doug. Can you give me a sound check? Do I sound
Yep,
okay?
I can hear you, Doug. You sound good.
Okay, good. I have my headset on.
So he can see you.
Oh, yeah. Corey, that Blazing Skull is Mason Ray.
All right, we'll change his name once he's in. He's coming in and out.
Oh, okay.
Okay, and turn on your video. Okay, sorry.
Give everybody a few more minutes here to get in. How's everyone doing today? It's Thursday. It's nice out. Jeff's got his puppy again.
Hey, puppy.
Is it potty trained yet?
Yes. He's very
That's
good.
good.
She's a good girl. Big fat belly.
How was your trip to the UP, Corey?
It was good. Went up to Pictured Rocks for a few days, and actually one of the people that were up there is actually an alumni from Rush that I met up with, having first time meeting that individual. I went kayaking Pictured Rocks, but it was surprisingly packed. Lots of people.
You camping?
Yeah, we rented like Airbnb. I think there was like 6 of us or something like that. All just chipped in and stayed there for the weekend.
Oh.
Sky, you back in Kalamazoo? You still in Traverse City?
Oh, I'm in Kalamazoo. My time in TC on the way back from North Dakota was really brief. I was there for 36 hours. So
Just for a moment.
yeah. I'll probably head back up there. I'm down here to write a bunch of thesis stuff, but once I'm into editing and finalizing, I'm back up there. So enjoy the fall colors.
Yep. All right, so today's plan, Doug is at the build facility. He's there with their waving. I'll make his screen prominent once he gets rolling. We're gonna go over the basic tools that we use and how to abuse them and not abuse them, and everything we have in our toolboxes. We're gonna have both programmers and build watching this because it's something that everybody should learn and get familiar with. This is a life skill to use in all places, how to use a screwdriver. Doug, do you want to do a sound check here?
Testing. You guys hear me all right?
Yep, we're getting nods. Yep, we can hear you.
Nods? Okay, good.
Yep.
I put my headset on and I tucked it under my mask so that hopefully it's not all muffled and garbled and whatnot. So,
All right.
all right.
We are going to make you the spotlight video.
All
Is that
right.
Jerry in the background? Tell Jerry to be quiet.
Yep, Jerry he is trying to figure out how to get his GoPro webcam stuff fired up, and we may switch over to that video here shortly. But in the meantime, all I have is my laptop here, and I'm going to have to aim it around and kind of hold things up and talk to him as we go. Ideally, we'll have something better here shortly, certainly in the weeks coming forward, but as of right now, it's just the webcam building my laptop. Okay.
Okay. If anybody has any questions that come up, just go ahead, just put that in chat, and then Doug and I can see them, and we can address them.
Okay. Are we ready to get started?
Yeah, let's do it.
All right. Okay. Well, a couple of words. Corey is spot on. You know, if you're going to work in the technical field, whether you're a programmer, a builder, a fabricator of some kind, knowing basic hand tools is a very good thing. Yeah, it's just a general competence. It gives you confidence as a potential employee or somebody interviewing for a job, just knowing that you can come into a shop and not look like an idiot when you pick up a tool because you know its name, you know how to use it, how not to use it. Just generally the things that we're going to go over here. And it's one of the nice things about Strikeforce and the FRC program in general is it gets you exposure to a lot of this stuff early on. You know, you would think if you go and you get a mechanical engineering degree that they would teach you some of this, but I'm here to tell you they do not. It's a whole lot of calculus and physics and statics and dynamics and, you know, a lot of heavy math, but the basic how to work with your hand stuff is kind of assumed. And in this society today where we get out our wallet and our charge card and we buy everything, we tend not to fix a whole lot of stuff. It's a bit of a dying art, but yet it's necessary if you're really going to work in this field. So hopefully this is of interest and of use to you guys, whether you're going to be doing software or build. So speaking of the build team, you can kind of think of that as having two main functions to it. One is design, and that's what a lot of people think of when they think of the FRC build team is folks that are brainstorming and coming up with the mechanisms and all the rest of that. And design is certainly a large part of it. But to properly design something, you also have to understand the processes you have available to you and the tools you have available to you, all the fabrication techniques. Because, like, for example, Strikeforce does not have a CNC mill. So we deliberately go out of our way not to design parts that would require a multi-axis CNC mill. On the flip side, we do have access to some very good 3D printing technology, and we leverage the heck out of that. So understanding what tools and what fabrication processes you have available to you is part of, or it's almost foundational or necessary before you even get into the design part. So tonight, we're going to talk about the basic hand tools, fabrication techniques with the hand tools. Again, both for your own competence and confidence as a potential future employer or adult, and also because it helps you understand as you design things, what you're thinking about as how it's going to be built.
Is that what you're calling?
Is there a question?
I was calling because I couldn't log in. Oh, sorry. If our microphone's on, I'm turning it off. Sorry about that, guys.
All right, no problem. All right, so by way of orientation, let's start out by turning around here. This is the Strikeforce pick, okay? Mark affectionately calls that big thing in the back of the pick the beast. And we store all of our spare parts, all of our fasteners in there. There's a couple of big screens in the center that the software guys use when we're at the competitions. And it brings up all the diagnostics for the robots, the status and everything. It can run through routines there on the screen, or sometimes we pipe in, information from the live feeds on the fields. But that's the beast. And on either side of the beast, we have it kind of laid out as a horseshoe. You've got a toolbox, and on the other side, you have another set of toolboxes. And on top of those toolboxes, you got a couple of workbenches. And on top of those workbenches, there's some other things mounted, and we'll get to all of that in a few minutes. But this is what we're going to go through, is these toolboxes and what's in them and how to use them. So notice that these drawers have labels on them. Sorry about that. And we always set these toolboxes up the same way. This one over here is on the right side of the pit, and the stuff on the other side is on the left side of the pit. And we actually have all of our tools during our build season put in the same place that we're going to have them when we actually go to our competition. And the reason is in the heat of battle, when you're trying to find the a particular tool, you want to be able to go right to it and grab it, not go hunting around and trying to find it. Now, I got to do a mea culpa here. I haven't been in the shop in well over a month. Other people have been working in here, so some of these drawers might be a bit disorganized, but we need to be cognizant of putting the tools back in the right place and keeping things organized so that when we go to look for things, we can find them easily. And that's key. We practice like we compete, and part of that practice is keeping our workshop clean and organized so that we can find stuff. All right, so this first toolbox here, the top drawer is labeled screwdrivers. Now you open that up, there's a hodgepodge collection of screwdrivers in that drawer. I'm gonna pause a second. I'm gonna try to hook the camera up here.
How many USB ports do you have?
2, but I can pull this one out. That's for the.
All right. This is, we need an adapter for the GoPro stuff. That is a high-def Microsoft camera used to use for vision systems.
Okay, do you know how to get that swapping out?
Yep, it should recognize it, and where's your mouse at? Let's see, this is Teams, where is, select camera, Microsoft Live Cam.
Gary, your saturation's way off and you're underexposed.
Wow, that picture's awful.
It's an Instagram filter he's got going on right now.
Ah, yeah.
Wonder if his camera has a problem.
It's probably default settings. Probably not the camera.
Go back to the other camera and keep going. Let me get a different camera.
Okay, Jerry's going to go back to my computer. All right, so as I was saying, this top drawer, furthest out of the pit is our screwdriver. And there are a couple different gross classes of screwdrivers in here. We have your standard or slotted screwdriver. You can see it's got like a flat blade on it. And then you got a Phillips head screwdriver here, which has kind of, you know, intersecting blades, if you will, to come into a point. And obviously you want to use the right screwdriver for the job. So if you're using Phillips fasteners, you use a Phillips screwdriver. If you're using standard fasteners, you use the slotted screwdriver. Now, all Phillips screwdrivers are not the same. Neither are the standard screwdrivers. They come in different sizes and they come in different lengths. And it's important to try to get at least close to the right fastener screwdriver match. If you don't, you'll wind up very easily stripping both the screwdriver over time. Everybody probably could go to their basement and find a Phillips screwdriver where instead of being a nice trapezoid like this, or it's kind of scooped out, and it's because the edges are worn down on it where it's been spinning as people have been trying to use it. So you want to use the right size because that minimizes the likelihood of that happening. How do you know it's the right size? When you stick it into the fastener, it should go and almost bottom out so that tip is in the bottom of the little Phillips fastener, and it shouldn't be rocking all over the place. It should be a nice snug fit. Similarly with a standard screwdriver, when you put it in, the blade should be tight in the slot. It should go in and almost bottom out in that slot, but it shouldn't be able to rotate much in the slot. If it starts to cock in the slot, if you think about it, the pressure where the screwdriver kind of comes into contact with the corners is much higher than it would be as if the same amount of torque was put into the screwdriver and it was spread over the whole length of the slot. And that pressure winds up deforming the screw in that area and strips it out really quickly, okay? So it's important that you match the blade of the screwdriver with the blade of the slot so that it's their full length and it's not chucking around in there. Now, length I mentioned earlier.
For those aspiring engineers out there too, that analysis of what Doug was just talking about, I spent a lot of time in my job doing that analysis because it was very important for the mechanism that I work on. It happens all the time in mechanisms, that interaction that he's talking about.
For those that don't know, that was the voice of Rob Dowdy. He is one of the Stryker engineers on the JR team at Stryker.
Yep. Thanks, Rob. Okay, so here's another couple of screwdrivers that were in that same drawer, and it's at kind of the other extreme sidewise. It's a standard screwdriver and a Phillips screwdriver, and you can see how much smaller it is. And when it gets to be, you know, that big of a difference, it seems ridiculous that anybody would try to use this tiny little screwdriver to turn this kind of a fastener. But you'd be amazed how many times people try to use too big of a screwdriver to fit in too small of a fastener. And because it doesn't bottom out, it doesn't get that good surface area contact, the stresses get real high and it strips it out in a hurry. Okay, so it's a big deal to try to find the best screwdriver for the spot. Now, again, mea culpa here. We don't have a full set of all the different sizes of screwdrivers. We have the common ones we use, and it's probably good enough. Just find the one that's closest and use that. It doesn't have to be perfect, but you know, use your head. Don't grab the wrong one. If there's another one that's more appropriate sitting there. And if you find a screwdriver that is all worn over and stripped out, let us know and we'll go buy another one and fix that because it's bad over time. It's a runaway condition. Once it starts to strip, it gets bad in a hurry. Okay, I talked about length a minute ago. In general, the rule for using screwdrivers is that you want to use the longest screwdriver you can, given the access you have to what you're working on. And the reason for that is that if you think about, so my finger's the screw. If I put the tip into the screw, and you know, this is never perfectly aligned. You know, ideally you'd want the screwdriver to be perfectly coaxial with the fastener, so that as you turn it, you know, there's no wobble or, you know, mismatch where it's tending to lift out and want to strip that screw. You want it to be perfectly coaxial with it, but nothing's perfect, right? So, you know, back up a little bit. So if as I'm looking at this business end of the screwdriver down at the handle, and I get it a little bit off, So let's say I can eyeball it to within 1/8 of an inch up here. That 1/8 of an inch translates to much smaller angular inaccuracy than it would on a shorter, stubbier screwdriver. For example, this one here. So if I were to take this one and the handle shifts off of 1/8 of an inch, I get a much bigger angle misalignment on my fastener, and it's much more likely to strip out. So in general, you want to reach for a longer screwdriver that's the right size. You want to line it up as best you can coaxial before you start trying to turn it. If you don't follow those rules, you'll strip a lot of fasteners out. That's a pain in the butt. Once you strip a fastener, your options to remove that fastener get limited in a hurry. Often we have to go get a grinder and grind a new slot into it, or figure out how to grab a hold of it with vice grips. It gets ugly. Usually it involves mentors and choice words trying to fix that kind of a situation. But it can all be avoided if you use the right screwdriver that fits the slot or the fitting. Use a longer handle if you have room to use it. Make sure it's lined up and bottomed out in that fastener before you start trying to turn. The next thing is screwdrivers, ultimately what turns the screw is called torque. It's force applied at a distance. And these handles aren't all that big, okay? So the force you apply tangentially with your fingers is what's generating that torque to move to spin the fastener. You got to grip it really hard so your hand doesn't slip on it. Sometimes it's useful, especially, matter of fact, some bigger screwdrivers, I don't know if we have any here, are set up. The shaft of the screwdriver is actually set up with flats on it, and that's so that you could actually get a wrench on the side. And with the same amount of force, you can generate a lot more torque because you're off of the axis. So you could put a wrench on there and push down with one hand and turn with the other. Sometimes that's really helpful. Generally speaking, you don't want to try to clamp vice grips on these things because it mars them all up, but that is potentially another option. One other thing to keep in mind with screwdrivers is before you just try spinning real hard, press down, because by pressing down hard and then turning, you're engaging those the tips with the slots or the driving features to the best advantage. So there's some tips on screwdrivers. Hopefully I'm not beating that to death, but I guess one other thing here on the stubby, if these are so bad, why the heck do we have them around? The reason we have them around is that sometimes there's not room to get access to a screw because there's something above it. You just can't get down in there in it. And this is all, you have to kind of sneak the screwdriver in there and then your fingers on it and try to turn it. In general, if you're in a situation where you have to use a stubby, it's because the design engineer didn't do his job particularly well. As a designer, remember I talked about how you got fabrication and it needs to be, or design needs to be fueled by knowledge of fabrication early on. That's one of the things I meant to kind of point out here, is that as you're designing things, it's best if you're going to use screws to give access for a screwdriver or whatever you're using to turn that fastener. Maybe it's a little, maybe you can't avoid a plate above there, but you could put a hole in the plate above the screw lined up on it. So you got access to the fastener to get down there and turn it, right? So that's screwdrivers. A couple other things in this drawer that we're showing here just because. One of them is called a Wago tool. Let's see if I can find it. Looks like it's missing. Okay, no, it's here. And essentially, it looks like a slotted screwdriver, but it's been bent. Well, why do we have a bent screwdriver? Piece of trash. Why is that in our screwdriver box? Excuse me, I'm chewing on my microphone here. The reason is that this is actually not used as a screwdriver. It is for working on the power distribution panel. It's a little pry bar that's designed to get in there and move the little spring contacts aside, so when you shove the wire in, you can lift it up while you shove the wire in, and then you pull this out and it clamps down on it. So it's kind of a specialized tool, but we keep it in the screwdriver drawer because it looks like a screwdriver. All right. Pliers. In the pliers drawer, we of course have pliers. These are called slip jaw pliers, sometimes called plumber's pliers. And notice on the side here, there's a slot. And when I put it on one side of the slot, the jaws don't close all the way, even with handles all the way together. And on the other side, they do. What's that about? What that is about is that when you're trying to use a set of pliers to get on a nut to hold on to it, remember that contact area I just talked about with screwdrivers? Well, you're trying to come in parallel on the flats, because if you just come in on the corners of the flats with a taper, it tends to want to spin out on you. So if you're trying to grab a bigger nut with these pliers, you want to be slipping that over. And that allows you to come on more parallel on the side. They're not truly parallel, but that's what that's about. In general, plumber's pliers are a bit of a tool of last resort. We use them to hold on to hot things. We use them sometimes to hold on to a fastener. But in general, we have better tools for the job. We have them around, we use them occasionally, but don't get in the habit of using plumber's pliers to hold on to nuts. Better, much better to use regular wrenches, which is the next door down. Before we go there, this is kind of a similar tool to the plumber's plier, sliding jaw pliers. And notice as I change that, I can get on a bigger nut and keep it more parallel. See, I can keep, you know, when you open it up, you can push it along in that slot. See how that works? But once it starts to come down, it stays in a particular slot, and you can adjust these to get close to a nut size. And again, there's better tools to hold on to nuts. But if you're holding on to a piece of sheet steel or you know, something else, occasionally a nut, you can hold on to this a little bit, but be careful because it's awful easy to strip out nuts with these. We have various different needle nose pliers in here. And it's pretty obvious why it's called needle nose, especially when you look at the smaller size ones. And these are useful to get into tiny spots where you have poor access and hold on to something, or to pull a dropped nut out of a nook and cranny, that kind of a thing. However, this is a good example of leverage. If I take a set of plumber's pliers and I put a given amount of force down here on the handles, that creates a torque around this axis, okay? So force times distance creates a torque around that axis. That same torque is wanting to pinch these closed, and because the distance from the axis is shorter, you wind up with much more force. That's why you can hold on to, you can crack walnuts with this. You could break your finger really easily with not a whole lot of force down here on the handles. Ow, 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 okay? And it's because there's a multiplication factor. If this is 4 times the distance from here, from here than it is from there to what you're holding on to, you're going to have 4 times the amount of force that you're putting into down here. You get 1/4 of the distance moved, so it's not like you're creating energy somehow. You're just transforming through leverage this force into a higher force. Big movement, small movement. That combination is the magic of pliers, if you will. Okay. Now, given that, we come back over and we look at needle nose pliers. What's the problem? I only have maybe 3 times the distance here versus that, if I'm maybe not even that much. So I can't generate anywhere near as much force out here on these tips with a given amount of input force as I could with the plumber pliers. Anybody follow that? So although needle nose pliers are useful for getting into small spots, they're not your tool of choice for really trying to hold securely onto something. Better than nothing, but you know, pliers with more leverage would be appropriate for most applications if you don't need to get in there. Here's some really tiny little needle nose ones. The ratio is a little better on that. These here called vice grip pliers, and they have a cam action that after they close, they go over a top dead center point and they lock up. So you can clamp that onto something, use it like a handle. You can well, you can almost use it like a portable vise, thus the name. Once they clamp on, and the way you control that clamping is by spinning this wheel down here. So I can actually tighten this to the point where I can't close those handles completely without, there, you heard it snap hopefully. Now that's locked up. It's cammed over and it's loaded on the nut. To get it off, you pinch that little back thing here and it pries it off past that center point. If you wanted to clamp onto something bigger, you spin that nut and it would come down and do that same function, but on a bigger rod. Right? So that's a vice grip, useful tools.
Hey, Doug, I know you touched on this very briefly, but do you want to talk about the shape of what you're holding on to, i.e. a piece of sheet metal versus a nut, and how round things versus flat things?
You can go with
Yep, just a second. So it looks like Jerry's got me set up.
That
with
is
the
your
camera.
camera, so you can take that wherever.
Okay, super. All right, I think what this guy's getting at is on these plumber pliers, you had an opening on here that is roughly ovoid and it's serrated. And there's actually a couple of them if you look close. There's a smaller one and a bigger one. Whereas on some of these other pliers, it's more parallel jaw, especially if you use it properly and slide it out so that you're more closely conforming to the shape that you're trying to clamp onto, like the parallel sides of a nut. If you're trying to hold on to a pipe or a piece of pipe, you know, this would be much more appropriate. Picture like a 1/2 inch diameter piece of pipe, plumbing pipe that you're working on. Again, plumber's pliers. These are something in between. They've got a little bit of a rounded area in the back end here, and they're more flat or straight up here. The front tips would be better to hang on to the flats of a nut or a piece of sheet stock. The back would be more appropriate for hanging onto a rod stock of a pipe. Similarly, here's a specialty kind of vice grips. We call these sheet metal pliers, and they have kind of a duckbill on them. And we use these all the time for sheet metal fabrication. And they work very similarly to a regular vice grip, only they spread the load out across these long edges. So let's say I have a tab on a piece of sheet metal that I want to bend up, and I want to do it nice and controlled, but I don't have a brake, which is the larger tool that you would use generally for sheet metal fabrication. I'd go ahead and grab this. I would put it on the sheet metal and I would adjust this down here until it just clamps on nicely and cams over without totally crushing it. And now I've got this nice distributed grip on the sheet metal. And let's say it's a piece, or it could be acrylic. I'll heat it up with a flame or with a hot air gun. And it's hot enough that I don't want to be in there with my fingers, let alone trying to grab it, you know, right tight up against where I'm trying to bend it. I can do it with this. And then once it's hot, I can bend it over. So these sheet metal pliers we use a lot with acrylic, or we'll use with sheet metal. Notice also that they are kind of bowed here. There's an opening. That's not a mistake. They do that intentionally so that once it's clamped down on the center, those are actually flatter and they more evenly distribute the load across those grips. So is that kind of what you're getting at, Sky?
Yes.
Okay. All right. Another thing that's in this plier drawer is snap ring pliers. These guys have these little tips on them. Sometimes they're bent at right angles like this. Hopefully you can see that. Other times they don't have the bend on them. But in any case, this area right out here at the tip, there's these little pins. And those go in something called a snap ring. And we'll talk about them a little bit more when we get over to them in the miscellaneous fasteners drawer. But these tools live in the plier drawer and they are for taking on and removing snap rings. Notice that there is a little adjustment on the side here. And the reason you have that is with a snap ring, it's really easy when you're taking them on and putting them off to overspring the snap ring, and then the snap ring is ruined. They can only take so much stretch elastically without plastically deforming. Those are two engineering terms. Elastic deformation, you can stretch it and it comes back to where it started, like an elastic band. Plastic deformation, it's like a piece of taffy. You stretch it and it never comes back again. It's plastically deformed. Well, snap rings are designed to be only used elastically. open up just enough to get into their spot to hold on to the thing they're trying to hold on to. But if you overstretch them, then they're no good, they're ruined. This little thing right here limits how far you can separate the tips of the snap ring plier, and you're supposed to adjust that so that it limits the maximum pull open on the snap rings. And that'll make more sense when you see a snap ring in a minute, okay? I think it's okay. Thank you. All right. There's some other things in this drawer that shouldn't be here. Let's see. This is sort of supposed to be here. This is a very specialized tool. It is for doing safety wire. Safety wire is a tempered steel that we use quite a bit on the robot for various different things. The name comes from the fact that it was developed for machinery where you wanted to make sure the nuts never came off or spun off under vibration, such as in an airplane or on a race car engine. They wind up wrapping this wire through a hole in the nut and the bolt and then twisting it. Now it can't, because it's kind of cross-pinned, it can't come unspun. Or they also weave it in and out multiple fasteners and they lock down the fasteners so they can't come undone. We do that occasionally on our robots, but more commonly we use the safety wire to tie things down, like a pneumatic fitting, for example. And the reason is we could take a loop of that wire around something. Let's say you have a nipple on a pipe and then a tube comes over the top. We put a piece of safety wire around it and then we grab onto that where the safety wire comes together with this, and then we twist the wire by pulling this handle in the back. These lock down on the wire, and you pull that. It's like an old-fashioned Yankee screwdriver, and it spins it all up. And as that wire spins, it wants to shorten down and constrict like a boa constrictor, and it makes a good seal. And it's also a good safety repair, or excuse me, a quick pit repair kind of thing that you can do. At a competition, if something breaks, you can put a splint across a broken bar, for example, safety wire on both sides of it, and that'll lock it down nice and tight. A lot of times you don't have time for super glue or epoxy or fabricating a new part, and you can fix a lot of things with safety wire because that wire's stiff and strong and you can crank it down really tight. So those are in here. All right, wrenches. We keep them in sets. There's two different kinds in here. There are metric and English, and there are, I guess another kind would be a crescent wrench. The crescent wrench is probably the thing that is most overused because it's easy. You just spin this little knob on the side, you fit it to your nut, and away you go. It's better than the plumber pliers. So if you use this over the plumber pliers, good, but it's nowhere near as good as the proper wrench. Because these crescent wrenches, they usually don't fit up quite right, and this head is big and bulky, so it's hard to get in tight spaces. And it generally has some slop in it, so it doesn't hold on to the nuts quite as well. It's far better off to take the appropriate wrench. You can see how the head is a whole lot trimmer than that for roughly the same size opening. I can get this into a smaller spot. Got a longer handle, stronger. It's machined precisely to have, very parallel sides on it that fit exactly onto the nut. You get it in there, and you're not going to bugger your nuts up with this. So proper wrench for the job is good. One of the things, speaking of competence and confidence, is pay attention to the fasteners we use. We tend to use 1/4-20s, 1032s, 1024s, and 832s, and we'll talk about what those mean in a minute. Those are the size fasteners we tend to standardize on our robot, and those fasteners tend to have the same nuts all the time. They're kind of standardized, and learning that so that it's intuitive kind of gives you a feeling of confidence and competence that you know how to work around the shop. Having to try 2 or 3 different wrenches to get to the right one just doesn't look good. It's not awful. Everybody does it, including me. But the longer you work at the stuff, the more confidence you get in that, and it looks good. When you're done with the wrenches, please put them back in the organized holders. That helps us find them a lot easier. If you open this drawer up and there's a pile of wrenches in there, and in the heat of battle you're trying to fix something, it makes it really hard to find the right thing. But if they're organized, much easier. And you can see we're not perfect about it. There's a few loose wrenches in there. But in general, that's what we ought to be aiming for. I will mention that we have some metric things around. In general, we don't use metric on the robots much. And you should not be using either the metric Allen keys or the metric wrenches unless you're sure that the fastener you're working on is metric. Sort of fitting wrenches are not good. Sort of fitting wrenches strip out the fasteners, and then you have a real problem on your hands trying to get it out once it's stripped. So find the right wrench for the right fastener you're working on. Don't use a sort of kind of metric equivalent. Not a good idea. All right. Allen keys. This is our Allen key drawer. And there's two broad types of Allen keys. This is called an L set. And the L sets are because they're shaped like an L. Okay. The drivers look like a screwdriver. We also, I said two, there's actually more than that. We have ones that are driven by socket wrenches, which we'll get to in a minute. And then we have the T-handle sets up here. And the T-handle, again, is because it has a T-handle on the top. So when do you use what on what? This is a little less stringent than what I was talking about with screwdrivers. You do need to make sure you're using the right one for the size of the fastener you're working on. But after that, it's really kind of depends a lot on access. If you're working on something deep in the bottom of a hole with lots of stuff around it, these guys are very convenient. In fact, we even have extensions we put on them to reach down into the bottom of holes to get fasteners that are buried in the robot. Again, from a design standpoint, it's bad to have a design where your fasteners are buried too far, but sometimes it's unavoidable, and this is what you do to deal with it. Just like a screwdriver, these have a limit on how much torque you can apply to it with just your hand. Whereas these guys, you can put a big socket wrench on it with a big handle, so you can wind up putting torque on it nicely. Similarly, the L's, the reason they are L-shaped is both ends are functional. You got the long straight end to get into tight spaces and to start, because you can spin them in your fingers nicely like this. But then when you go to torque the fastener down nice and tight, you use the other end, provided you got access. And now you've got leverage to create torque on that fastener and get it sucked down. Now, notice, go ahead.
Keeping in mind that L-shaped, when you use it with the short end on the fastener and the long end as a lever, you're applying a heck of a lot more torque than you would with a screwdriver. So just keep that in mind.
Yes, particularly with the small Allen key drivers, you can generate way too much torque than the fastener can take. In fact, we go through tons of these little Allen keys here every year. We replace them periodically because the ends get rounded over. And once these little corners get rounded over, it might as well be trash. It's useless. We'll sometimes cut them off, but you're kind of fighting a losing battle, because as you cut them off, it yields the steel next to it, and it's soft after that, and it's just a runaway problem. So we usually throw them out after they start stripping and buy new ones. One thing I'll point out is our best sets are actually color coded. You see this paint pen marking on there? That was done to try to keep the sets complete. At the moment, this is okay. There's a few of them missing in here, but ideally I would look in the drawer and all of my yellow Allen keys would be in the right, appropriate slots. There's yellow, there's red, there's a blue set in here, and then there's some unlabeled. And I get it. We get in a hurry, and it always doesn't go back, right? We're realists around here. But if you have the time, it's a good idea to clean up after yourself and get them back in the right set. Keeping organized helps us work efficiently. There are a couple other ones in here which have like tape specifically put on them. And these are because they're special guys. This one has been ground down so that you can get into tight little places and use it as an L with leverage. This, and I think, I don't know, there's a specific place where we had a problem with it. Where was it?
It was,
Yeah, it was a robot specific problem, but again, a design issue in the end of the day. This one here is a Torx Allen. It's kind of a special animal. This was size for size 2 screws. We were playing around last year with using size 2 Torx fasteners to hold together some rollers. I think we actually wound up going that way, but that was what that was. This one is called a Super Torx. I don't know if you can see it, but it's almost like a flower shaped on the end of it. And this has more contact area than a regular Allen key, or way more than a Phillips head would have on it. And that allows it to take more torque before stripping. So that's what that's about. It's not, you know, interchangeable with a regular Allen key. So we're just kind of kicking around in the front of that drawer there. All right, we mentioned sockets earlier. Here's our socket sets.
Hey Doug, before you move on to the sockets, we had a question in chat on the safety wire. Do you need to have a pre-drilled fastener to use safety wires on them?
If you're going to use it that classic way I talked about, where you're cross pinning essentially with the safety wire, the answer is yes. Although I suppose you could cross drill your own fasteners. That's typically not the case. Usually there are special nuts or castellated nuts that are used along with that technique. We don't typically use that on the robot. Honestly, we're kind of abusing the safety wire the way we use it because it works so darn well. We don't often safety wire our nuts like you would on a race car or an airplane. I'm just kind of giving you that background to know where it came from. Good question. So here's our socket sets. And this isn't like your dad's set, which has, you know, 150 of them or whatever, of all sizes up to, a couple inches, because our robots don't have anything that big, nowhere near that big. In fact, this is more sockets than we need. We could probably narrow this down to like 6 sockets and we'd have all of our needs covered. But they come in a set, so we keep it in a set. This has a driver on it, and it fits into a little socket on the back of that socket there, and you can use it like a screwdriver. Or you can take it and put it on a socket wrench if you have the access to get in there and do this. And now you can tighten, and so long as you hear a click, you're making progress. If you don't have enough angle back and forth to get a click, you might as well stop if you're not getting any more out of that. But if you have a 5 or 10 degrees and you're hearing that click, you're working that fastener down. There are some other things in here. This is a universal. And you put that in between your socket and the driver, and that allows you to get off axis. I mentioned how important it was to be on axis with the driver. This would be the tool to allow you to make an exception to that. You don't want that in there unless you have to, because it does cause some other issues. You really can't get as much torque into the fastener efficiently. But if you're dealing with a place where you can't get on axis quite right, the universal is the solution to that. I'm making a mess. This is an extension, again, to get down into places where you don't have room. And we have some longer extensions in here. All right, so there are metric sets, there are English sets, and there are even Allen sets that are driven by socket. I showed you some of the longer ones earlier. Here's some shorter ones. These are all to drive metric and English Allen keys with the socket wrench. We also have, kind of in the wrong drawer, but we also have some nut drivers, which are kind of like fixed sockets on the end of a screwdriver handle. Some more extensions here. Okay. Then we have this thing called the mechanical drawer, which is a bit of a catch-all. In there, we've got a hacksaw. I'll mention on hacksaws. These are actually, they don't feel like much when you run your fingers against them. They feel kind of safe because the teeth are so small, but they're fairly sharp. And you can, and often do, cut yourself if you get carried away, sounding like crazy through something and you run your finger against it, it'll cut you pretty good. So don't just assume because it doesn't feel that dangerous here that you can't cut yourself with it. But you can. I
Cut
have.
yourself with everything here.
Yep. Speaking of hacksaws, almost never a good idea to be trying to saw something in your hand. Much better off to come up and use the vise. This is a nice vise. It has some jaws that are magnetically fixed to it, soft jaws. Or if you're trying to hold on to something that you don't care about much, you can come right down to these serrated steel jaws and crank down nice and hard on it. Once your hand, once the thing you're trying to work on is nicely secured, whether you're drilling or sawing or whatever, it's a whole lot easier. Instead of moving your arm around and losing all kinds of control, it's all now locked down. You can focus on nice, smooth, even strokes with a hacksaw. So speaking of that, that is the key to a hacksaw. You want to get your piece locked down. You want to make sure that the force you're putting into this is right along the blade, not cockeyed. If your blade starts getting pushed sideways, the kerf, which is the area which has been removed by the blade, the kerf will pinch and drag on the sides of the blade, and you will burn all kinds of energy and get nowhere. So the whole key to using this properly is to have your strokes nice and long and smooth, right in axis with the blade. Let's see, what else can I tell you about this? This is a pretty nice hacksaw. You might run into other hacksaws where there's adjustments on the blade tension. You want these things nice and tight, because again, if they're not tensioned properly, they tend to take on an S shape as you're working with them and pinch in the kerf of the saw. So the key to working with a hacksaw properly, again, is nice, smooth, not a whole lot of pressure going down, nice, smooth, long strokes using the whole blade and making sure that it's in line with the blade. Generally speaking, you start a cut with the draw until you get a kerf established. So you lift up and down, and then once you got a kerf, then you can kind of go back and forth. And that's about it on hacksaws. All right, this is what the safety wire looks like. It's down in this drawer. You can see it's just a spool of wire. This is an abomination, but nonetheless, every once in a while it's useful. It's a hacksaw blade and handle, and you can see how it was all bent and it's floppy. You can't put tension on that blade. It's very hard to control. So it is useful for kind of laying down and cutting a fastener off when you can't get at it any other way, but generally not the tool of choice. What do we got? Oh, it's a super skookum set of screwdriver bits. You'll find that these will fit into one of the nut driver or the handle that was in the socket set. They'll fit into that. And because there's a whole lot of them in here, you'll find the right one for the job. If you're struggling with a fastener because we don't have a screwdriver that fits quite right, guess what? The right one will be in the set. You just got to find it. And let's make sure they get put back when we're done using it. So there's Torx, there's Super Torx, there's every, Allen, there's every standard blade, there's every Phillips blade, there's even square drive. There's all kinds of cool things. All right. This, one of my favorite tools. This isn't a hand tool, which is, or it's, I guess, a power hand tool. Call this an oscillating saw. And this blade here goes back and forth like that, very fast. How fast? Well, it depends on how you have this, depends on how fast you have this dialed up. And that's a good, I guess, point to mention. If you're cutting plastic, it is very easy to go too fast. What happens when you go too fast? Well, the blade, I got to fix my microphone, sorry. The blade has friction unintended as it's cutting, and that friction builds up heat in the material, and it will melt the plastic. And it gets all gummy and you have all kinds of problems. So there is such a thing as having this thing too fast. Plastic in particular would be a case for that. Another reason you might want to turn your speed down is something called resonance. These teeth are all regularly spaced, and this thing is running at a set speed. So it is putting in vibratory inputs into the thing you're cutting in periodic motion, okay? And there's a characteristic of structures that they tend to have think of it as a tuning fork, a frequency that when you excite them at that, they resonate and they start to flop all over the place. And sometimes when you're cutting on something, you'll find that you'll get into a resonance situation and it's really hard to control. So change your speed a little bit. That's the easy thing to do. Or let up a little bit. That's the other way you can handle that. Pay attention to the blade on this. They can and do dull and the teeth break off, or they like melted aluminum will get into there and foul the teeth. And when that happens, you're just wasting energy and you're not going to be able to do good work. If you're having trouble cutting, stop and look at your blade. Speaking of cutting aluminum, you'll learn that as we talk about using the power tools more. But aluminum is one of those things where you don't think of it as melting. You know, heck, it's a metal. Well, it does under the forces and the heat that you generate with cutting with a power tool. And it will foul on a drill bit. It will foul up in the teeth of the saw. And the way you avoid that is having the speed proper and also lubricating the blade. So the most common thing we use with aluminum around here is WD-40. We just give it a little spritz. You don't have to soak it, but the WD-40 reduces the friction and keeps you below that point where the stuff starts melting on your blade. So there's various different blades in here on this. They're all in the bottom here, and just poke around and look. There's also a head on it that will allow you to use sanding pads. Not that we do a whole lot of sanding around here. Buffing, very useful tool. You can slip this into little tight spots, kind of like you might use that bogus handsaw handle thing to do stuff. You can sculpt sheet metal with this. You can cut fasteners off, very useful.
Hey, Doug, can you show us how to change one of those blades on that?
Yep, I should have done that. Okay, this lever on the top, you flip it up. See how that, it just flips up and then it rotates. And if you go counterclockwise and you spin it off a little bit, that blade will just pull straight out. Put it back on, you snap it in, and you rotate it clockwise. And you just snug, doesn't have to be overly tight, snug, and then you fold it down. And now that blade's in there, right? Notice that you can mount that blade at an angle. It doesn't have to be straight on. Have a nice trick if you happen to have a place where you're having trouble getting access to. Now, all of our power tools, you need to be wearing safety glasses when you use them. You need to be aware that you can, and if you spend enough time with them, likely will cut yourself or pinch yourself or whatever. So treat them with respect, and stakes go up when you add power to the equation. You guys are welcome to use this tool, just don't abuse it, and be aware it can hurt you if you don't treat it with respect and use it properly. Safety glasses with any power tools, whether it's drilling or sawing, grinding, all of that. Always use safety glasses. Hand tools in general, you're supposed to have safety glasses on anytime you're in the shop. We're not Nazis about it around here. This is the time I'll give my situational awareness speech here. It is far more important that you're paying attention and you're aware of what's going around you than to have some magical safety glasses on your face that are going to protect you from all harm. Safety glasses are good things. I'm not belittling them. They have their place. They're very useful. They can preserve the only two eyes you have. But don't assume because you're wearing safety glasses that something can't come in from the side or spear you in the side or hurt you in some other way. A lot of teams, they wear their safety glasses like they're some kind of a magic shield, and they're just not. So I would rather have you, oops, occasionally and not use safety glasses while you're using a freaking screwdriver than have your safety glasses on. They're all covered with grease and smeared, and you're not paying attention to what's happening around you and your peripheral vision and stuff. So I don't want to beat that horse too much, and I'm a bit of a different opinion relative to FRC in general. And in fact, when we go to competitions, you have to have safety glasses on anytime you're on the robot or in the pits. But here within our build space, I'm a little less stringent on that, particularly with the non-power tools. Use your good judgment. What I won't tolerate is people screwing around, not paying attention to surroundings, and being aware when the robot's firing up, that kind of stuff, because that will get you hurt. All right. This here is a roto tool, sometimes called a die grinder. It's another power tool. It spins very, very fast. It has little bits that go into this end of it. You don't see the index here. We'll find that in a minute. But this up here, it's called the arbor, and there's a little collet inside of it. You have to have, there's different sizes of these collets that have to match the shaft of the thing you're putting in there. Okay, that goes in, your cutter goes in, then this comes down on top. Now, how do you tighten that down? You have to press this little button right here while you're turning that. Otherwise, you know, whatever you're putting in here is just spinning the motor. It's not tightening that collet down. But that collet, you can look at it, see how it works. It's a very common design in machine tools. It's just slightly bigger in diameter on the inside than the thing you're holding on to, and it has intersecting slits that go across it, so it has compliance. And then there's this taper on the end of it. On the inside of this piece is another taper that matches that taper, so that when you screw down on this, it collapses those slits on the side of the spinning part, and it clamps down on it. And because you're dealing with fine threads, a reasonable amount of torque here can create quite a bit of compressive force on that interface, so it sustains torque and won't slip and spin on you. So that's how you change the cutters on this. This here, that's your on-off. Back here, it's variable speed again. Same deal you do. Cutting aluminum or cutting plastic, turn the speed down. Having a resonance problem, a control problem, instead of always assuming you can go faster, try going slower. You might find out it's easier to control, actually. Same thing with the WD-40 cutting aluminum. A lot of times we do little trim jobs on aluminum with this, and we'll lubricate it with WD-40 to get that job done. Very useful tool. There's also, around here somewhere, over there I think, a battery-powered version of this, which is nice because it doesn't have a cord on it. This is called a jigsaw. Runs like this. We often use this when cutting plastic or aluminum sheet. What's nice about this versus some other saws we have is the blade is relatively short. Now, it's not long this way, which means that you can cut curves. You can imagine if this was a great big long blade, it gets stuck in the curve and you can't cut curves. So we have a selection of these, including some that are even narrower than what is in here right now, for cutting curves in plywood or plastic or aluminum. And this one I don't believe is variable speed. Some of these things are, but this one's not. So it's just got an on-off trigger up here. If you're going to be doing a lot of cutting, you can pull it in and you press that button on the side and it'll hold it on. The blade change on this is toolless. Just pull that up right there, and the blade will pop out. Put it back in, you kind of reverse that. The foot on this saw is adjustable for angle. You get where the fastener is, but you loosen it faster, and then you can cut an angle through whatever you're cutting on. This is baling wire. It's kind of a poor man's safety wire. It's an annealed wire, and we use this for quick repairs sometimes. It's even downer and dirtier than safety wire repair, but it has its place. It's useful. Similar, we have Kevlar cord. All right, back to this vise real quick up top. I mentioned these jaws earlier. So that you don't mar the thing you're working on. In general, we have those jaws in place. If you look at them from the side, there is a V here. If you're putting a piece of round stock in here, you'll notice those V's will kind of line up and across from one another. You put your round stock in there and that'll clamp down nicely and hold your round stock better than it would, and less likely to crush than if it was on flat and flat. There's also you look at it from the top, more V's in here. Same reason. So instead of trying to put your round stock out this way to work on it, you want to hold it up straight, you put it in those notches, and that'll hold it for you nicely. All right. This guy, this normally also lives down in the mechanical tools. This one, unless you're a senior and have been around a while, I really don't want to see you use it. It's probably the most dangerous tool that we have in the shop. It's called an angle grinder. At the moment, it has a flapper wheel on it. We also have abrasive cutoff wheels we put into it. It is an extremely useful tool. It's probably Mark Wasserman's favorite tool. He loves the angle grinder. But he'll also repeat the words I said earlier, most dangerous tool in the shop. This thing spins at, I don't know, 18, 20,000 RPM, and it's got a lot of inertia wound up in that motor when it's running. And it's like when something goes wrong, it's like instantaneously bad juju. So it's a very good tool. You can shape things, you can move a lot of material in a hurry, you can cut steel with it. I really, please, if you're new to the team, just call a mentor if you think you have an application to use the angle grinder. Unless you're like a senior that's been around a while and you feel confident you understand what's going on and the potential danger of this thing. It is not, it's no joke. Therefore, I'm not even going to go over it anymore. Don't want to tempt anybody. I'll tell one anecdotal story about that. My brother, my big brother, 3 years older than me, was out on an island up in Alaska using an angle grinder, grinding some steel one time, and it got away from him, and it came back and hit him in the groin right here. It was a 1/4 inch away from hitting his femoral artery, and he was on his own out on the island, and he would have bled out and died, just like that. And that's not a happens every once in a blue moon kind of thing. It can happen. Mark will tell a story about how he was using one, and his shirt got wrapped up into it, and it came back and was right next to his abdomen, and he was screaming like a little girl, is the way he puts it, in perfect Mark Wasserman language. So anyway, no joke. Those are great tools, but you got to treat that with a lot of healthy respect. Okay, this is a heat gun. It is what it sounds like. I will mention there is an adjustment for temperature on the back. You rotate it to raise or lower the temperature. Switch on the bottom. There's a high and a low speed. I don't know if you can see it online, but the lights flickered when I did that. It's because this draws quite a bit of current between trying to power the blower and the heating elements in it. We have some tips around here someplace to focus or distribute the hot air coming out of this. What we use it for is like softening plastics before we're going to bend them, or heating up a Loctited fastener to break that Loctite down. Shrink wrap is another place we use it for. It is no joke really hot. This will burn you pretty good if you touch it. So just be aware of that. It's also a potential fire hazard, even though there's no flame. It gets hot enough that it's sitting next to paper wood, it can flash something off. So you guys are more than welcome to use this. I just want to let you know that it's not entirely safe. You have to pay attention. All right, moving on over, we have various different drills around here. We have, in general, standardized on the DeWalt battery chargers, which are on that thing over there, kind of color-coded. However, there are different voltage tools, and they're labeled on the side. This one says 12 volts on it. There are 20-volt ones over there. You got to get the right battery pack with the right handpiece. Thankfully, DeWalt has made it so that they don't fit. But if you're wondering why the yellow battery pack doesn't fit in the yellow tool, it's because you got the wrong voltage. Okay? There's a little button on here, not to insult anybody's intelligence, but it goes from side to side. That reverses the drill. Okay? When you're going in, the right-handed people, your index finger's on the right side, you want that thing pushed in, and that's drilling or turning a screw in. If you're trying to reverse it, to clear it, let's say it's caught on something, you can press it or take a screw out, you press it on the other side so it's coming in where your thumb is, and that will reverse the motor and come out. The switch up top here changes the gearbox inside from low to high speed, and that just changes the ratio of the gearbox in here so that in high speed, you can go higher, you can go faster, but you can't generate as much torque. But if you're with bigger fasteners and you need more torque and less speed, you can go down to the slower speed and get it in there. Because they are battery powered, they can and do run out of juice if it's really bogging down, even in the low torque setting or high torque setting. Try a new battery. We have other batteries. Get something that's got charge in it. So I think that's about it. Oh, one other thing. This front here, you'll notice right on the top, there's a little arrow and it's lined up with something that looks like a drill. That means that this is in drill mode. It doesn't have any slipping engineered into it. It's meant to hold on to that drill as best as it possibly can in the Jacobs truck. If you rotate that collar, you've got different numbers that show up. When you're all the way down on one, it'll almost immediately slip. It'll go brrr, it kind of rat-a-tats almost. That's intentionally slipping in there so that you don't over torque your fastener. You can put power drivers in this to drive screws, you know, Phillips bit or a slotted bit or whatever, and you will intentionally set this at a lower torque so that you don't strip the screws out as you bottom them out. Okay? So that's what that's for. What number is the right number? You kind of play around with it until you get the right feel. You don't want to strip your screws, but you want to drive them in all the way. Once you find that number, you just leave it there, and that's what you use it for. Generally speaking, though, we leave it on the drill setting. All right?
Doug, one last thing. Keyed chucks versus keyless chucks, and putting drill bits in them, just like changing a fastener.
Yep, good point. The way these work, you can see those three little pieces coming in and out on the side as I spin this. This is a keyless Jacobs chuck. There's also something called a keyed Jacobs chuck. A keyless Jacobs chuck, there's no thing here, no separate tool to tighten that down. You take a drill, use an aircraft drill so you can see what I'm doing. You open it up so that it's bigger than the shaft, you stick it in, you spin it down, you kind of feel it. It needs to be coaxial with the motor arbor, okay? So you're kind of rock it around and let those jaws come down evenly on it. Once it's in there, you grab it with your two hands, tuck your elbows in, and you twist it. And that'll crank down those three pieces on there with a lot of force and transmit the torque from the drill into the shaft. I cannot generate as much force doing this as I can with the keyed chuck because I have additional mechanical advantage. And I'll show you that when we get to it, I guess. So if you're having slippage problems, either A, try getting stronger with your keyless chuck, or go get onto the drill press or something that has a keyed chuck, and that'll help a lot. But both of them are Jacobs chucks. They work similarly. It's just you have more mechanical advantage on one versus the other. It is easy, especially with small drill bits, to have the drill bit get off of center and into one of these slots, especially if you're going hard and fast and not paying attention. It's pretty easy to do this. Okay, now that's a rather gross example, okay? But we've all done it at some point where the drill is not quite in alignment with the arbor, and you fire this thing up and it goes wumpity wumpity wump. Stop. Okay, you're going to break the drill bit. You're not going to be successful drilling an accurate hole. Stop. Loosen it up. Get it coaxial. Wiggle it around as you tighten it down. It should be nice and straight in line with the arbor. If you're seeing any kind of run out, wumpity wump, stop and fix it. Okay? All right. Measuring devices, next drawer. So this is the next tool chest, top drawer. A number of good things in here. All right. This is called the speed square. And it has kind of a T on one end so you can stick it up against the edges of things. And now this is perfectly at right angles to that edge. Cut things off as a square. Generally, this is a tool that we use with sheet stock or with wood fabrication or building a field, that kind of thing. It's not something you use when you get into fine fabrication. It's just not a precise enough instrument. Terribly useful for raw fabrication, but not so much to build up construction. Okay, this is a set of calipers. It's kind of almost the opposite extreme. It is highly accurate, measures down to usually the thousandths of an inch. Okay, this particular kind is a set of digital calipers. Obviously, it's got digits up here, it's electronic. The way it works is there's a magnetic strip in here that has a code embedded into that magnetics, if you will, that's read by the head on this. And it's calibrated so that when you put something in between these blades up here and just come down until it just touches it, not crushes it, but just touches it, it'll tell you what the distance is between them. So my fingertip is 0.494 inches, or just under half of an inch. Okay? It's 0.500 would be half an inch. Now, there is a 0 button on here. Sometimes they get out of 0, usually because they've been dropped or forced. You can re-zero it here. Or let's say you want to go a half an inch over this thickness or whatever. I could re-zero it there, and now I can move my bars to a half an inch. 500. Okay, and now that's half an inch thicker than my thumb. And in fact, if I were to come down here, I'd see I'd be in the negatives. I'd re-zero it. Okay, I can also change it from English to metric by pressing that button up here. Again, we don't do a ton with metric on our robots, but it's occasionally it happens. When you're done with it, please turn it off. Some of these are auto off, most of them are not. Batteries wear out. Those are precision instruments. Please treat them gently. Tape measure. Everybody knows about tape measures. Everybody's played with tape measures. Everybody's been yelled at by their dad for playing with a tape measure. Okay, same thing here. Mentors will yell at you if you sort of play with their tape measures because they get ruined. You can see this one has already gotten kind of buggered here on this front edge. It's not bad enough that we're going to throw it out yet, but it's in the candidacy. Okay. When they get played with, they get messed up, and then a measuring tool that's messed up is no good to anybody. Okay. So, yes, they're fun. They have auto retractors in them. They're tempting. Don't do it. Okay. This is a little ruler, but a really nice little ruler that's measured in super fine graduations on here. We use this for manually laying things out all the time. This is a machinist square. It happens to be a low budget, rough and ready machinist square, but a square nonetheless. We kind of use it a lot of the times like we use this guy. You can set it up, actually this one can't. My other one you can set up on a 45 or straight in. It has the level in it. Let me get my good one out to explain a couple finer points of that though. In this box, this magic red box, is a good machinist square set. Notice, I just put that blade right in there like magic. I guarantee you, if I took 100 people off the street and gave them the blade and this body, and I told them to put the blade in there, 99 of them would just get frustrated and not be able to figure it out. The secret is, and this is one of those things that you can immediately gain competency or, credibility, there you go, around a machinist. If they ever see a plan with one of these, if you put it together immediately, they go, yeah, that guy knows what he's talking about. He's somebody I can actually have a conversation with, right? If you look in here, and unfortunately this is going to be tough on the video, in this slot there is on one side or the other, and it can be flipped from one side to the other. There's a little half moon shaped thing. It's flipped from one side to the other by this wheel, okay? In real life, you can see down there really easy to see it. That little half moon thing rides in this groove on the rule, okay? The groove needs to be on the same side as the half moon slot. Even if it is, blade's not going in, okay? But notice, this thing is sprung. I push it up, and now it can go in. And that little springiness means that I can move this around and the blade doesn't drop on the ground, okay? And then when I want to lock it off, let's say I want to measure out repeatedly 3 inches, I set this on 3, tighten it down, and now I got a square I can walk around it and repeatedly measure out 3 inches anywhere. Okay, and I can loosen it up, move it again. I can take it all the way out. Again, if I just try putting it in there, it's not going. I push it up and it goes right in. If I have the groove on the wrong side, I can push it up and it still won't go in. Everybody get how that works? It's not magic, but knowing that little thing will actually gain you credibility. All right, this is actually a fairly expensive machinist square set. If you're doing rough and ready woodwork, use the cheap one. If you're doing finer layout stuff on a robot, feel free to use the good one, just don't abuse it. Put it back in the box when we're done. There are two other heads in here. There's a protractor head for accurately laying out angles. And there is a centering head which allows you, when you put the blade in, to mark, you can put this on a circle, and put a couple of lines across each other that'll set the center of the stock on the circle. So for example, if you're going to use the lathe over here, which we'll get to in person, probably do training in person on the lathe, you need to potentially know where the center is of a piece of round stock before you put it in the lathe. If you're going to set it up with a 5-center dead center, that would be how you would do that. Okay. What other magic do we have? We got another set of good calipers. We've got a ruler. We have a fish scale. Sometimes our mechanisms, we want to know how much force we're springing them down with, for example. That's what this is for. We have distance, non-contact distance measuring. We should have in here levels. I don't. This is a screw sizer. If the screw fits in the particular hole, then you know what size it is. You can't recognize it by eye. Let's see.
To go back to your screw sizer, that screw sizer that you had, that's actually for lining up transferring holes from a versaplanetary gear set, as far as if you have 1 stage, 2 stage, or 3 stages.
Oh, okay. I'm sorry.
That's okay.
There are other things that look just like this that are what I said they were. Yeah, these are jigs or fixtures that have been set up to help you drill holes in the right place without having to go through the trouble of using my machinist square. That's what they're for. Thank you, Corey. All right. There's a fancy level in here. I don't see it. It's probably out somewhere. Metalworking. All right. Number of things in here. Let's start off with drills and tacks. The next drawer down has all of our regular drills, our drill indexes, these guys, and we'll get to that in a second. In the metalworking drawer, we have sets of drills with taps. What's a tap? A tap is how you cut threads into material so that you can thread a screw into it. Now, I'll pull one out so you can see what that looks like. This is a bigger one, so it's really easy to see. So it's kind of serrated. So serrations are not a helix. The edges are actually quite sharp, and they will cut your way in. Once you drill a hole in the material, you put this in and follow it down that hole. It will cut the threads in so you can actually put it faster. Use them all the time, all over the place. Okay? There are different kinds of taps. We have sets in here with the different kinds of taps by size. And along with those, we have the tap drill to make the starter hole. So I don't want to see people taking, because they can't find a 3/16 drill for whatever reason. Okay? They can't find it in the drill index because somebody didn't put it back. I don't want to see people coming into the tap and drill indexes and grabbing a drill that's sort of kind of 3/16 and using it. This is a drill specifically sized as a starter drill for these taps. Okay? And it's in good condition so that it makes the right size hole, it's sharp, and we want to keep them together as a set. So this is not to be used as a substitute for a missing drill out here. So they live in there in these pockets with the appropriate taps. Now, if you look at the ends of the taps, one of them is more tapered than the other. This one here can be used to start holes and to do through holes. However, if you're going to do a bottom hole, which is a hole that doesn't come out the other side, just a blind hole, and you want threads all the way to the bottom, You have to start with this one and then switch over to this one. You have the threads go all the way down to the tip, and it's kind of square at the bottom versus tapered. You can see how the threads wouldn't be fully formed at the bottom of the hole if you stayed with the taper one. Trying to start tapping with a bottoming hole tap is a nightmare because it doesn't want to start straight. It wants to go all over the place. You start it with the other one and finish with this. So those are the good tapping drill sets. There are a couple of them in here, even labeled on the top. Return all drills immediately after use for tapping only. Hopefully this is all clear. All right. This is our better set. This is our rougher set. Same deal, but for general purpose, grab this first. If you're doing precision work though, the other one's not going to be Nazi about it. All right, four things. This is a deburring tool. After you drill a hole, it often has a burr on the side of it. Stick this there, press down and twist it a few times, and take the burr off the hole and make it nice and smooth so it doesn't cut. It is able to be extended. There's all these little divots on it, so you can set it to different lengths. Usually we just leave it choked up. So that's that. This is also a deburring tool, and it could be used in a bigger round hole, but more commonly this is used for openings like in trusses that we have made at water jet that have sharp edges on it. You hold this and you run it around the edge and it will peel off almost like a potato peel, the little sharp burr that's on the edge of the metal. Yes, excellent point. This is a pretty safe tool, but it is a blade. And if you get careless with it and carried away and going too fast and cutting towards yourself, it can and will bite into you. I've done it. It happens. It's not the end of the world. You're not going to bleed out. It's not the angle grinder, but it can cut you. These are tap lancers, and we hold on to the taps when we're tapping holes with these. When we actually get into fabrication, we'll show you a few tricks on starting taps straight, because if you don't start a tap straight, it'll keep on going crooked and make a mess. I'll also talk to you about feeling the tap so you don't break the tap. Anything that's cut metal tends to be very hard. Anything that's very hard tends to be brittle. So if you over torque a small tap, it can and will break, and then it's stuck in your hole and you're pulling hair out because your part scrap at that point. So knowing how to feel the tap and knowing how much torque you put on it, when to go in and then back out, clean the tap so that it doesn't bind up, those are all things you kind of have to learn by feel. I'll mention them here now. We also sometimes start with a drill press so that we make sure that we're getting the hole started straight. This here is a brooch. I'll just mention what it's for and I'll show you how to use it when it comes time. If you look at this thing in cross section, not on the ends, but just inside, it's hexagonal. And what this is for is taking a round hole and turning it into a hexagonal hole. So if you think about it, it's relatively easy to make a round hole. You take a drill bit and put it in a drill and spin it. And because it's axisymmetric, it peels away the hole and you have this round hole. But how do you make a hole that has sharp corners in it, whether it's a triangle or a square or a hexagon? How do you do that with a spinning tool? Not easily. There are ways of doing it, but not in this shop. And the way you do it in this shop and most places is you use something called a brooch. You drill out, it's almost like tapping in a way. You drill a pilot hole and then you come in that pilot hole with a brooch. This pilot's in that pilot hole. In this case, it's a 1/2 inch hole. And then you press this through a piece of material. And each one of these is successively a little bit bigger. And it's almost like a saw stood up on its edge at right angles. So it's like saw teeth. And it winds up taking little nibbles at first and widening that hole out until it's a hexagon hole. It has nice sharp corners. Why would you want a hexagonal hole or a triangular hole or a square hole? Because you want to drive torque through that. So we often have shafts that we want to put into a drum and want to drive the drum. This is how you use like a 1/2-inch hex shaft, drive with a gearbox, and then the mechanism has a hex bowl fabricated this way.
All right, Doug. I think we're gonna pause you there.
Okay.
So it's 7:30,
Okay.
and then we can
Yeah.
resume this next week if I think it's a good time.
Yeah, that's actually really good. And sorry if I'm droning on, but trust me, the stuff that I'm saying, most people really, they think they know it, but they don't really know it. And you need these skills and this knowledge and this terminology to have confidence in the shop, not hurt yourself, do good work, and to have street credit. All right, sorry, I lost track of time.
Oh no, not at all. It's 7:30 is a good time to wrap.
Yeah. Yep. Any questions before we knock off?
Okay, I'm gonna pass it over to Brianna. She's got something she wants to show everyone real quick, and then we will call it a night.
All right.
All right, thank you, everybody.
Thanks, Doug. That was super awesome. I learned a ton of stuff. Like,
Good.
I never had someone tell me like the
That
differences
worked okay?
between different
Was
wrenches.
that good to have
That's
something we
great.
could move around?
All right.
All right. I forgot to
So-
get over you to share screen again. I did it last week.
Oh, yeah, you disabled it.
Are you able to share screen?
Nope.
Okay.
I probably can turn on my video. Hello. Y'all might be able to tell I have a theme for the thing
There you are.
that I'm
Here,
about to
let's
talk
do this. I
about.
can just make you the spotlight video. You know, to even share. Oh no, you need to share your screen. Oh.
Oh yeah, it works. Okay.
Well, we can see you, but we can't see your screen.
Well, I'm sharing it. Okay, there it goes.
There it goes.
All right. So I was out for a walk last week. I was seeing Halloween decorations come out, and I was like, hey, how are we going to have Halloween safely this year? And what are some things we can do as engineers and technical folks to create some safe Halloweens for kids? So I thought of an idea of maybe we could create designs or even mechanisms to distribute candy safely to kids on Halloween. So what we're going to do is we will be posting our ideas on this Google Drive, and you get bonus points for if you build it and bonus points for creativity. So if you have come up with a theme or a story, or maybe your the way that you give candy is like involves some sort of a riddle or a trick or scares people. I think this could be really fun. So some of the rules are you must deliver candy in a sanitary fashion. So no kid should come in contact with the candy distribution system or source.
I'm not too hungry.
And
Like, just
someone is
couple-
not on mute.
No, it's okay.
Hi. All right. All right. So also social distancing applies. So if you're the one handing out the candy, I hope you're in a hazmat suit, which could be a very good Halloween costume. So don't kill anyone. I think that's key. If you're going to launch a projectile, please make it low energy. We don't want to cause any 2-year-olds to lose their eyeballs, you know. And yeah, even if you have a vendetta against the neighborhood bully, now is not the time to release it. And so we'll be posting our ideas here. I'd love to see pictures of your designs, you know, just like Little sketches are fine too, and we'll post that on October 22nd, so right before Halloween, and we can see. So I have a little example of a idea that I came up with. It's called the cat smack. So it's a cat on top of a wardrobe, maybe a black cat, spooky, and it smacks candy on into the candy receptacle of the trick-or-treater when they press a foot pedal. So something really simple, like maybe there's like a piston that is actuated when you press on the foot pedal. You could make it out of like pop bottles or something like that and tubing. And the candy just falls from a bucket. So if a kid keeps pressing the foot pedal and tries to keep whacking candy into their bucket, they'll eventually run out. So you can just refill it. So it's like something like that, like something simple, and maybe it could be used for future candy distribution systems for other Halloweens if you build a good design. And maybe it could be used by other people in your neighborhood as a way to spread the Halloween cheer safely. So yeah, that's it. So can't wait to hear ideas. Hope people enjoy this.
Thank you, Brianna. It'd be fun to see what people come out with and give everyone a chance to kind of share and see what's going on. At-home projects to do. All
Yeah,
right,
you
everyone.
guys can get your hands dirty while we can't actually be in the workshop. So yeah.
Yep.
All right,
Yep.
go ahead.
Nope, good job. Thank you, Brianna. That Google Drive, does everyone have the link to that? Or do you need to send that out?
I think Shelby created a link, but I guess we would have to say, oh, hi. We'll have to send it out.
Okay. Yeah, we'll send that out in the Google group email so people can have a repository to put their stuff. All right, everyone. Thank you. We will continue tools part 2 next week. The session is recorded, so I will be posting that through this weekend that you can share. Well, it'll be a private recording that only if you have been shared the link you can see for those who are not able to attend or left early to go have dinner. Rob Downey. Okay, everyone. See ya.
Takes so long to leave Zoom meetings.
Yeah,
You got to press so many buttons.